Okay, so when is that packet due again?
Thursday.
Right, our test is what, next Thursday? Is that right? Let me see. I brought my calendar today. Oh no, it's due on the day of the test, which is November 1st. Unless we move it. We'll see how things go. This is number 18. And you're asked to factor, right? So first thing we look, GCF, there's no greatest common factor. So we count the number of terms. We have 3 terms. So we're going to try that method where you take the number in front, the number in the back. You multiply those two together. You get -10. Then you look at the number in the middle, -7. And you try and come up with 2 numbers that multiply to be -10 and add up to be -7. And this is where you had a problem, or?
I got 5 and 2.
Okay, but you couldn't get the signs to work out, right? So like 5 and -2 or -5 and +2 are the only ones that even have a chance. You could look at 10 and -1 and -10 and +1. None of these add up to be -7. So what do we do? What do we say? Prime, right? That's what I told y'all in class last time. You just say it's prime, and you're done. Okay? Means it doesn't factor. It doesn't factor with any methods that we have. All right, 19, did you have the same problem with 19?
Yeah.
Okay, so if you can't find the numbers, and this is, I think, pretty obvious, hopefully, to you that these numbers just, you're not going to be able to come up with them, so you're done. Any other questions? That was 18 and 19 have been covered. Yes?
I have a question on 1 for the graph on the homework.
On the homework? Okay. What page?
Page
55?
55.
Okay. So it says use the graph to determine the values of the function, right? So which one of those did you have a question on? Which number? Number 1? Okay, so it's going to be tough for me to draw this. I'll do my best. Comes down, comes back up, comes up, touches here, comes back down, back up like that. This is at 2, this is at 3, this is at -6, this is at -2. Is that good enough to go off of? Okay. So the first question is find f of -2. So just remember that whenever you see f of something, this is actually the y value of the point, and here they're giving you the x value. So they're saying when you plug in -2 for x, what is the y value of that function? So go to -2 on x, which is this point right here. What's the y value, the up and down value here? 0. So this should be equal to 0. F of 1, right? Is that what they're saying? F of 1 on the next one? F of 1 is not so obvious. You have to kind of guess from the picture. Like here's 1, right? You have to kind of like guess where that comes over, like what's that y value of that point. I would say, I don't know. You could argue that with me. Anywhere between, my picture would be better. What's that?
Because the answer is weird. That's
What does the answer say?
It's like -3 over 2 or something.
-3 halves, which is -1.5. So, yeah, they converted, I mean, just to a fraction. They said this is -3 halves, which is -1.5. Which I think if you look at the picture, it kind of looks like it's about halfway between -1 and -2. On your test, trust me, I will make it where you can, it'll be very obvious where the point is. I won't make you guess like this.
Because they go something like a number 4,
4, f of -10. Whoa.
Yeah.
Yeah.
Like, how would you find -10?
Yeah, that's messed up. Yeah, I would just, yeah, I'm going to make a note on that. They're taking edits. The people who put this packet together have asked for edits, so I will, yeah, so throw that one out. You could say maybe, well, no. Yeah.
That's wondering how you estimate any values of x.
Yeah, okay, so like number 5, it says, where is f of x equal to -3? So when they write this, and this is important when you come in to take the test, they're actually providing you the y value this time. And they're asking you for the x value. So it looks like this. When y is -3, what is the x value? So you'll have to look at the picture and kind of estimate where is your function -3. So you'd go down to -3, which let's just say is here, -3. And that happens, you have a point here and a point here. And you have to estimate what the two x values are for those points. So I would say for -3, wait, was it -3 or +3? Yeah, I'm doing number 8. Man, again, we're going to estimate this. This is not a good problem. I'm just going to circle this whole problem. What they should do, let me do something else. How about I put a different problem up here? It's more like the test. And that way you can see like it's not going to be hard to read. All right? And then we'll go through and I'll do one of each of these, or a few of these, so you can see what to do. So look, let's say we have, I'll do the graph in a different color. And so what I'll provide you on your test is there will be these very light dotted lines that will kind of grid this out for you so you can see where things are. Does that make sense? I'll give you some very light lines like this. And then I'll draw a function in here for you. So let's say, something like that. And then we'll make this, this is 1, this is 2, this is 3, 1, 2, -1, -2, -1, -2, -3. Make sense? And then I could ask you something like, what's f of -2? So you see it's going to be much easier for you to tell what's happening here. This means you're going to be plugging x in, is -2, and asking what's the y value. So you go to -2, what's the y value here? 2. Much easier to read. If I say this, f of x is, let's go with, well, -3 won't be on there. Let's go with -2. How about that? So that means you're looking at where's your y value, right? Your y value is -2. That would be here. So what x coordinate is that? 0, right? So this would mean x is equal to 0. Does that make sense? Does that help? Do you see how it'll be easier to read? Okay. Is that clear for everybody? Sure? Sure. Okay. All right. Let's get started with today's stuff. We are going to be solving quadratic equations today. But before we start, we need to get a couple of things in order before we begin. So I'll first start by reminding you of what we call the perfect squares. Okay, the perfect squares are all of your common counting numbers squared. So everyone here should be comfortable with the idea that, of course, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. And I think we went through this before. I said you should probably know up to about, what, 12 or 13? 4 squared is 16, 5 squared is 25, 6 squared, 36, 7 squared, 49, 8 squared, 64, 9 squared, 81, 10 squared, 100, 11 squared is 121, 12 squared, 144. That's about usually what we'll see, but we'll throw a few more. 13 squared is 169, 14 squared is 196, and 15 squared is 225. 225? Yeah. You should know those. I mean, the thing is, we need to recognize, like, if we ever see the number 81, we need to know that that's 9 squared. If we see the number 121, we need to know that that's 11 squared. Now, the reason why this is useful is because when we take numbers like, let's do the number 12, right? We can always take 12 and break it down into it's called the prime factorization of the number. What we do is we try and come up with two numbers that multiply to be 12. So can we think of two numbers that multiply to be 12? You could do 6 and 2, right? You could also do 12 and 1. You could also do 3 and 4, right? Everyone agree with that? Of those options, I just heard you say 6 and 2, 12 and 1, and 3 and 4. Of these options, do any of these options contain a perfect square? 3 and 4 contain a perfect square, right? Yes? Or 3 times 4, or 3 times 4 is 12, and there's a perfect square. So what we're going to be doing today when we solve quadratic equations is within the problem, we're going to have to take square roots of numbers. And when we take a square root of a number, we're going to want to break it down into pieces. And those pieces that we break it down into, we want one of them, hopefully, to be a perfect square. All right? So this is just to get us thinking. Those are your perfect squares. This is how we break a number down. Let's try and find perfect squares when we break numbers down. All right, so let's talk about square roots. We're still not solving equations yet. Square roots. If we write the square root of x equals y, what we mean is that when we square y, we would get x back. Now, I know that that looks weird, but let's write down an example underneath this. If I write the square root of 9 equals 3, that's because if I take this and square it, I should get back what was underneath this square root symbol. So when we say square root of 9, we mean what number times itself is 9, right? What number times itself is 9? 3. And if we did this for all the perfect squares, we'd get nice answers, wouldn't we? Like the square root of 121 would be 11. The square root of 144 would be 12, right? So on and so forth. But what happens when we get to something like 12? What if we have the square root of 12? Well, there is a number that when you multiply times itself, you get 12, and you'd have to get on your calculator to get that. So if you have your calculator, why don't you try that? What's the square root of 12? You should get a decimal on your calculator. It should be approximately, you should be getting 3.464, and it keeps on going, right? Which is fine. That is an answer. But what we want to do is, instead of going to our calculator, we want to have the ability to break this down further before we go here. So I'm going to rewrite 12 as 4 times 3, because we just said it was 4 times 3, right? And I could write 3 times 4 or 4 times 3, either way. Always write the perfect square out in front of the other one. It'll help you out on the next step. So do you agree with this? This root 12 is equal to root of 4 times 3? Yes? And now there's a property of roots, of square roots, that says if you have multiplication inside, you can split this into 2 separate roots and then multiply those 2 answers. So this is an important property from here to here, that you're allowed to do that. And then when you look at each of these individually, right, what's the square root of 4? 2. So you get 2 and then times root 3. So what I'd like for you to do is on your calculator, I'd like for you to take, oh, by the way, does 3 break down anymore? Does 3 break down? Just to 3 times 1, right? So once we get this to a number that can't be broken down anymore, we say it's prime and we're done. So at this point, we can't take that down any further. And on your calculator, do square root of 3. Forget the 2 for right now. Just do square root of 3. And you should get like 1.7 something. Now multiply that times 2. And you should get this answer. All right, you should get this. So all I'm trying to tell you is that the square root of 12 we already knew was this, but if you rewrite square root of 12 in this form, right, it's the same answer. This right here is called the exact form. This is the exact, and then this answer right here is the approximate answer. APP, approximate. What I'm going to want you to be able to do is both. I'm going to ask that you can get both the approximate answer and the exact answer, and I want that exact answer worked out. Like, don't leave this, go down to here. So let's practice a few more of those, just so we're all on the same page. How about square root of 18? So you look first, 18 obviously is not a perfect square, right? But is 18 something times something with 9 times 2, right? So I can rewrite this as square root of 9 times 2, and then I can use the property of radicals that allows me to split this into 2 separate ones. And notice also again, I put the 9 in front of the 2, because I told you if it has a perfect square, put that in front. And now what's the square root of 9? That's 3, so 3 root 2. And 2 cannot be broken down any further, right? So we're done. Questions? All right, let's do another one. Square root of 45. So can you break 45 down? 9 times 5? And then you split this up into 2 roots again. This is going to be very similar to the last one, right? What will it be? 3 square roots 5. 3 times root 5. So the numbers I've given you so far, 12, 18, 45, most of those you can do in your head, just 9 times 5, 2 times 9, 3 times 4. Let's try one that's a little harder. Root 72. That might be harder, may not, depends on you. So what's the first thing that comes to mind when you see that? 9 and 8. 9 and 8? Most of you thinking 9 and 8? Okay, so let's do square root of 9 times 8, and then that's square root of 9 times square root of 8, which would at this point give you what? 3 square roots of 8. Now, are we done though? No, because that 8 actually breaks down itself, right? The 8 can be rewritten as what? 2 times 4, which I'm going to write 4 times 2, right? Same thing. So we're not done here. This is the part that you have to be careful with. You have to know when you're done. I'm going to rewrite 8 as 4 times 2. And then I can split that into 2 pieces, right? 2 different roots. 3 times root 4 times root 2. Bless you. And what is the square root of 4? 2. So this is 3 times 2 times root 2. And you can actually multiply the 3 times the 2 and get what? 6. So this will become 6 root 2. Now, I want to show you on this same problem that you might have noticed this, maybe not, that you could have rewritten 72 a different way to start. You could have said it's 36 times 2, which it is, right? And if you do it this way, see 36 is a perfect square. And so you could have gone straight to the next step, which would have been square root of 36, which would have been 6, and then root 2. See, and we kind of jumped over that, having to do it twice. So my recommendation to you would be, when you're looking at a number and you're not sure, start dividing this number by perfect squares. And try and get the largest perfect square you possibly can. Now, I'm going to do an example so you can see what I mean. I'm going to do 980, root 980. Yeah, square root of 980. So here's how I'm going to approach this. I have all my perfect squares in my head here. 4, 9, right? What are they? 4, 9, 16, 25, 36, right? I can keep going. See what I'm saying? 49, 64. I'm curious if any of those go into that. So what I'm going to do is, on my calculator, I'm going to start dividing 980 first by 4. And so it does go into that, right? I take that, divide by 4, I get 245. So I know 245 times 4, I'll put the perfect square out front. I know I can do that, right? I could do that. But maybe there's more I can do. So let me go and do 980 divided by 9. Doesn't go in perfectly. I get 100.8 or 108.8888. So I'm not going to use 9. How about 16? I get 61.25. That's not a nice number. Do y'all understand what I'm doing? Yeah. You sure? I just keep dividing through. How about 980 divided by 25? 39.2? No. 980 divided by 36? No. 980 divided by 49? 20. 20, right? So I could do, what did I divide by? I forgot, 49? So 49 and 20, right? I could do that. So I think, would you agree that's a little easier to work with than this one? Because then on this one we'd have to try and break the 245 down, continue. Do you think you're going to have any trouble breaking 20 down? Probably not. So I think you get it to a point where you feel comfortable working with it and then continue. So I'm going to rewrite this as square root 49 times square root of 20. I kind of skipped the middle step. Is that all right? I broke it up right now. And that's going to be 7 root 20. But I'm not done because 20 breaks down to be 4 times 5, right? It's 4 times 5, and 4 is a perfect square. So I'm going to have to do a little bit more work. 7 root 4 times root 5. Understand? I broke the root 20 into 2 pieces. And root 4 is 2. So you get 7 times 2 times root 5. And this is, what, 14 root 5? What was the, I stopped on this list, but what was 14 squared? 196. If we would have kept going here, all right, I stopped at 49, but if I would have gone all the way out to 196, if we take 980 and divide it by 196, I would have got 5. And then, do you see, I would have been at this stage already. So it just depends on how far you want to go in the perfect squares. I stopped here because I was happy with being able to deal with the 20. All right, what do you think? This okay? All right, now we need to talk about one more thing with square roots before we continue, and that is, what is the square root of -1? How many of you have seen this before? Yeah? This is a problem, isn't it? This presents an issue for us, because we know a couple of things with arithmetic, that if you take a positive number and you multiply it times another positive number, your answer should be what? Positive. And if I take a negative number and multiply it times a negative number, I should get positive, right? And because of this, if I say, let's just say that I call this answer y, okay? I'm telling you that there's an answer to that and it's y. Then this means that when I square y, I get what? -1. But what's wrong with saying that squaring a number is -1? Think about it. Y times y is -1. That's what this says. Well, y is the same thing as y, right? So y could be positive or it could be negative. If y is positive, what's a positive times a positive? Positive, so it can't be negative, right? What if y is negative? A negative times a negative should be positive, right? We shouldn't be able to do this. Do you agree? You should not be able to multiply a number times itself and get a negative number out. So this actually presented a huge problem for mathematicians for many, many years, for many hundreds, many thousands of years. And then somebody came up with the idea that we could assign a value to this. And what we call it is I, all right? It's not like x, okay? X is a variable, like x can be different values. I is the square root of -1. Have y'all ever seen pi before? Does everyone know that pi is just a number? It's about 3.14 something, blah, blah, blah. This is a number. It's approximately 3.14. There's some other important numbers in mathematics that we use that we put letters on. There's another one, e. This is approximately 2.718. These are important numbers in mathematics. And whenever we have really important numbers, we like to assign letters to them, all right? Pi, e. Now, this is a very important number in mathematics, and we assign a letter to it, and we say it is I, all right? The square root of -1 is I. And see, it's really hard for me to like stay on track when I start talking about I, because I did most of my graduate work and research and stuff in dealing with this sort of thing. So I kind of like it, but I don't want to talk too much about it. What I will say is this, that a lot of people that have been shown I have been told that this is called the imaginary, it's actually, this is the imaginary unit. I is the imaginary unit. And the bad thing about this is this word imaginary, all right? Because it makes you think it doesn't exist. It makes you think, you know, kind of like you have your imaginary friend. Everyone here has an imaginary friend, right? I'm the only one who has an imaginary friend? Okay. All right, so look. When we see that word, we automatically think like someone's making stuff up, right? Like, come on, you have an imaginary number. And that's because in the beginning, the first person who ever actually came up with this idea, a lot of mathematicians were like, what is this guy drinking or doing? Because this doesn't make any sense. We don't need to actually define this at all. And he was like, no, we can do it. And it wasn't until later on that we mathematicians were able to prove that this is real. I mean, it's a real thing. It's not imaginary. But that name kind of stuck. And here we are today, thousands of years later, and I'm still introducing it to you as the imaginary unit. So I wish it had a better name, but it doesn't. All right? So the problem is this. Excuse me. You've all heard this before, right? Real numbers. Let's just put all the real numbers in this big box, okay? Well, that's a circle, but there they are. They're all these numbers, right? These are the numbers that known your whole life, right? 1, 2, 3, -1, 1/2, 3/4, any number that you can think of. E, pi, everything that you've ever been taught. Square root of 2, anything, has always lived in here, right? But it turns out that this group of numbers actually belongs to a larger group of numbers, and these numbers are called the complex numbers. And complex numbers. And the only difference between complex numbers and real numbers is that the complex numbers can have the I also. So I can be included in the number somehow. I'm not going to get into details because this is not the place for it. What I'm trying to get you to see is this. I equate this to this concept of a fish bowl. You know, you have a fish, my daughter has fish. If you've ever owned a fish, that fish's universe is in that bowl, right? It has no idea that you have a dog in the backyard, right? Doesn't even know what a dog is, right? The universe for this fish is that bowl, right? Has no concept of it. Think about fish in a lake, right? Do they have any idea that there are goats living up in the hills, right? Well, it's the same sort of thing here. In the math classes that we teach, all right, even through calculus, we always stay here. We just stay in the fishbowl. And it isn't until after calculus, later on, that you actually step outside and they go, hey, guess what? There's a goat on the mountain. There's a whole other universe of numbers that we use to solve problems. And so they're very useful. A good example is when my brother was in graduate school, he's an engineer, he called me with a problem. He and his buddies couldn't solve it, and the problem was they hadn't done enough work in the complex numbers, so they were stuck in here. I was able to take the number and look at it through a broader spectrum, I always say through the goggles of complex numbers instead of real numbers, and the problem became trivial, it became simple, almost like laughable how easy it was. But if you're stuck here, you can't do the problem easily. You have to be able to look at the whole picture. So that's why I'm trying to say there's value to these things. They are not imaginary. They're not useless. So in this class, we introduce you to them, but it's really a poor introduction. All we do is we like open the window a little bit and we say, hey, look out there. Y'all look, and then we close the window and say, don't go back out there. All right? That's what we're going to do here. We're just going to say square root of -1 is I, and that's it. Okay? When you see a square root of -1, that's an I. Don't ask me about it. Don't try and get me to somehow make you understand the goat up on the mountain, all right? All right, so all we're going to do now is just adapt what we know already, and that's square root of -9 we can't do, right? Unless we bring the I in, right? So what I'll do is I will split this up. I'll write this as -1 times 9 because we all agree that -9 is -1 times 9. And then I will split this up into 2. And guess what? The square root of 9 is 3, right? But the square root of -1 is I, right? This is I. So this is I times 3. And we don't like to write it that way. We like to write it 3I. And we're done. Square root of -12. So this is square root of -1 times 12. This is square root of -1 times square root of 12, right? We did this problem earlier. What was root 12? Yeah, okay, yes, but get me to the answer. I don't want to go through the whole thing again. It was 2 root 3, right? 2 root 3? So this becomes square root of -1, which is I, times 2 times root 3, right? Like this. And the way that we like to write this, although that is correct, but we like to write it this way, 2I root 3. We always want to put the roots in the back. We always put the numbers in the front and I after it. So here we have 3I. We didn't have any roots, so we just wrote it like this. Here we have an I and a 2. We put those side by side, 2 in front of the I, and then our root. The reason why we do not put the I in the back is because somebody might think, or you may not write precisely enough, they might think that that root goes over the I. And so they may think that the I is inside. And the square root of I is actually something we could solve, but we don't do that, okay? We just do this. Are we good? Good? All right. Now we're ready to solve quadratic equations. All right, before we can solve a quadratic equation, we need to make sure we know what they look like. All quadratic equations look like this. Ax squared plus bx plus c equals 0. X here in the problem is the variable. All right, so our variable here is x. A, b, and c are numbers. So if I put some numbers in for a, b, and c, then I'd be creating a quadratic equation. Right now, the way it appears, this is what we call a general quadratic equation. Nobody has told me what a, b, and c are yet, so I can't solve it. There's one other additional thing. A cannot be 0. Now, why can't a be 0? If this is 0, right, then this doesn't matter anymore, does it? And so I could just erase that. And if I erase that, I no longer have my variable squared. And that's what it takes to be quadratic. Quad. 2, power 2 on the variable. This power has to be here in order for us to call it a quadratic. If that goes away, this doesn't have a 2, it's not quadratic. All right? This would actually be a linear equation. So that's what a quadratic looks like. And we have techniques for solving these, for finding answers. So we're going to start first of all with a special case. Case 1, b is 0. All right, so let's take a look at a quadratic. What does the general quadratic look like if the b is 0? Wouldn't it look like this? Ax squared plus c equals 0. Right, that middle piece, that piece that had bx would be gone, wouldn't it? And all you would have is your variable squared with some number in front of it perhaps, and then a number by itself. Let me show you an example right next to this. Okay, as an example, let's say we had 5x squared minus 36 equals 0. That would be a quadratic equation, wouldn't it? Where your b is 0. Understand? So when we say b is 0, could you also just, so you remember, say that you're missing the x term? Right? The x term is gone. You have an x squared term, but you do not have an x by itself, right? That's what it would mean to say b is 0. Now, the way that we solve these is pretty straightforward. It's the same thing we did with linear equations. We will, when we had a linear equation like this, how did we solve this? Add 1 to both sides, right? To get the 4x by itself, then we divide it by 4, right? That's what we did to solve this. When you have a missing x term, we're going to go through the same procedure as we did here. We're going to isolate this, get it by itself. So you would do what? Add 36 to both sides. And you would have 5x squared equals 36. You're almost there. Divide both sides by 5. Divide by 5 here, divide by 5 here. And we would get, on the left side, x squared. On the right side, 36 over 5. We good? Bless you. Now, bless you. That's what x squared is, right? X squared is 36 over 5. We want to know what x is. So to find x, we have to do something. We have to get rid of the squared. And to do that, we square root both sides. Does this look like something you've seen? X squared equals that. You take the square root on both sides. There's one thing I didn't do that's incorrect at this point. What do I have to do? What do you have to do anytime you take the square root on both sides of an equation? Anyone remember? Let me illustrate it over here. What if I told you right now that some number squared was 4? What's the number? 2. Is that the only number? I agree. 2 times 2 is 4. What else would work? Has to be the same number, though. What's that? Negative 2 times negative 2. Do you agree if I take negative 2 right in here? Well, let me do the 2 first. If I square 2, that's 2 times 2, that is 4, so that checks. But if I take negative 2 and I square it, that's negative 2 times negative 2. Negative times a negative is positive. And this would also be 4, right? So there are actually 2 possible answers here to this. They are 2 and negative 2, right? So the way that we account for that is when we come in here and we take the square root on both sides, I must do plus or minus. I must write here plus or minus, meaning that there is a positive answer and a negative answer. Just like over here, positive 2 and negative 2, that would give you the answer. So let me come back over here just so you can see it. If I did this over here, square root here and square root here, and I did plus or minus, then the square root of x squared would just give you x. What's the square root of 4? 2, but then you have plus or minus. So plus or minus 2. And see, that's telling you the 2 answers. It's positive 2 or negative 2. Got me? Okay. So x here equals plus or minus root 36 over 5. And I can do one more thing. Does anyone recognize that 36 is a perfect square? It's 6 squared. So I could do this, plus or minus with square roots. You are allowed to break it up. If it's division, you can split it into 2. And then I do the square root on the top, which is 6. And then on the bottom, I'm going to leave it because I can't break down 5. I'm just going to leave it like this. Is that okay? Looks weird? Now, I know some of you, yeah, that's a weird looking answer, but that's an answer. I know some of you from your past have been told that you can't have roots in the bottom. Anyone remember that ever? Can't have roots in the bottom. Who else? Show of hands. I just want to see if anyone remembers being told that you can't leave square roots in the bottom. Only 1, 2, 3 people, 4 people, 5 people, 6. Okay, that's not true. Okay, you can always leave a root in the bottom. There's nothing wrong with it. The reason why you're told that is most likely because your teacher was told that. And they were told that by their teacher. And they were told that by their teacher. But there's nothing wrong with it. Would you like to know why, or you care? Or? Yeah? Okay, there's a reason why. The reason is this. All right. So let's take an example here. 1 over root 2. You've been told you're not allowed to, you've been told you can't leave it like that. Do you remember what they told you had to do? Yeah, you would take this and you would multiply it by a 1, right? But that 1 is very special. It's root 2 over itself. That's a 1, right? And so what you get here on the top is 1 times root 2, which is root 2. And when you do root 2 times root 2, you can put the 2's together into one root, and then that's a 4. I know I'm making this more drawn out than it has to be, but I'm just trying to make sure you understand where all the pieces come from. These 2 roots come together into one root. 2 times 2 is 4, square root of 4 is 2, and you no longer have a root in the bottom, right? And then you're being told that that's good now. This is bad, this is good. Well, sorry, this is bad, this is good. If you were to get on your calculator right now and type these in, you would get the same exact answer. They're the same number. But you want to know why they told you this is bad, right? That's what you want to know. Here's why. Because before calculators, all right, before calculators, people were having to do these computations by hand, okay? So how would you do, without a calculator, 1 divided by the square root of 2? Well, you wouldn't, right? You'd give up. Here's the way it worked. Back in the day, there were a list of numbers that people just had to memorize. Like people had to memorize pi, and they would have like 3.1415, and they would actually have contests to see like who could memorize pi the furthest. One of my colleagues who's in his mid to late 60s right now, he knows pi out 120 digits, okay? Because he grew up in an era where that was like, that's how you measured your level of math dorkiness, was like, you know, how many digits do you know pi? You know, that sort of thing. I mean, seriously, it was like an ego thing. And there are certain numbers they had to know, like root 2, very, very, very common. Root 2 comes up a lot. So they'd memorize that, 1.414. And they would say again, okay, I know that out 60 digits, whatever. And so they had all these numbers that they just had stored in their brains because they didn't have a calculator to go to. Right? You okay with that part of it so far? I don't care about pi. I know pi, that's about it. I don't care after that because I grew up in a different generation. So, you know that there's a guy that knows this out like 60,000 digits?
What?
The world record? Yeah. Look it up on YouTube. Very interesting guy, actually. He doesn't look at numbers like we do. He looks at numbers like objects. So like if I asked you right now to like describe to me, if I asked you to memorize 60,000 digits, no one here could do it, right? But if I asked you to describe in detail what you did this morning, you could probably give me a pretty good detail. You know, I woke up, looked over, there's my nightstand. My nightstand's brown. I've got my phone there. My phone's laying down. I took it out of the charger. I got up. There's my door to my bathroom. Right, my door opens in. I know my toothbrush is there. I know my clothes are on the floor. I mean, you could describe in detail, right? A scenery, right? That's the way that he looks at numbers. It's like a scenery that he's just walking through. Each number is like a shape or an animal. It's really crazy. But okay, back to this. So this is it, right? These guys have all these things memorized. And then they get faced with this problem, okay? So they have to calculate this. And their teachers are telling them, no, you're not going to do this. You have to turn it into that. Here's why. If I try and divide this, then I have to go back to old school division. That means like division bar, right? Like if I do 12 divided by 3, I do, well, let's make it something else. Like 5, I do 12 here and 5 here, right? Then I say, how many times 5 go into 12? 2 times 10, and then I have 2 left over, right? Then I'd bring a decimal point in, and I'd bring down a 0. And I say, how many times does 5 go into 20? 4, so the answer is 2.4. That's old school division, right? Y'all seen that before? Let's try to do old school division on this. What would go inside the division bar? 1. What would go outside the division bar? Well, I'm a dork. I'm back in the different generation. I know that. I know it out at least 4 digits. Okay? With me? Yeah. Now, what do you multiply 1.414 by to get 1? I have no idea, right? Right? Like this. What do I multiply 5 by to get 12? Well, I know 2 is going to be a little smaller, right? 3 is too big. That's a very difficult computation for me to do mentally. Now, look at this one instead. This is the same number, right? Okay, what goes in the division box this time?
2.
Root 2, 1.414, right? What goes outside? 2. Now, does 2 go into 1? No. Bring the decimal point up. Does 2 go into 14?
Yes.
How many times? 7. You bring this down, 14, then you go through your work. It's much easier to do, and you get 0.707. That's what would happen if you do it this way. And this computation is so much easier to do by hand than this one, which is why they don't like roots in the bottom. But they is them, and we are us now. We don't care about roots in the bottom. Because if we have 6 over root 5, and they really want me to give you a decimal answer, I'm not going to do that. I'm going to go to my calculator, right? So, okay, it's an obsolete thing. I need to stay on task here. I'm sorry. Let's do another example. Let's do 6x squared plus 8 equals 0. So we are looking at a quadratic equation, right? It is missing the x term. It is missing the x term, right? When it's missing the x term, you just isolate, right? Isolate the x squared. So I'm going to subtract the 8. And I'll get that. Then I will divide by 6. So x squared is negative 8 over 6. That reduces, doesn't it? That becomes x squared is negative 4/3. Y'all still with me? Now what? Square root both sides. And when you come in and you take the square root, right? You break out the square root tool and hit both sides of it with it, right? You have to remember plus or minus. You've got to remember that. If you forget it on the test, points will be taken off. It won't be a 0 point. You won't get all the points taken off, but you won't get full credit if you forget plus or minus. And underneath here goes negative 4/3. Now, students in my Math 1414 class will lose almost all points if they forget plus or minus, because they're going to go build bridges one day. I don't want them forgetting plus or minus, right? I want that bridge to not fall. All right, so what now? X equals plus or minus. Now, can I split that root into 2 pieces? I could, and I'm doing that because 4 I recognize as a perfect square. And actually, it's negative 4, isn't it? Negative 4, great. What am I going to do there? Can I take the square root of negative 4? Yes, as long as I'm allowed to bring in the I. Am I allowed to bring in I?
Of course.
Of course. So let me just look at that real quick over here. If I just had square root of negative 4, you'd break that down to be square root of negative 1 times 4, which is going to be square root of negative 1 times square root of 4. That's what that is.
This will be 2i.
Just be 2i. So the top is 2i. So this should equal plus or minus 2i over root 3.
Is the plus and minus with the root 3 as well? Or just with the
It's out in front. It's just saying it's this whole thing positive or this whole thing minus. One thing to remember about fractions and negative signs is that when I write something like negative 1/2, that's the same as negative 1 over positive 2, which is the same as positive 1 over negative 2. These are all equivalent. So this plus here could be like plus the 2i and then minus the 2i, or you could do plus or minus down here. We just put it out in front. Gives us 2 answers. All right, do you feel like you understand the method for when you're missing the x term? All right. What about this next one? New method, case 2. C is 0. So this would be missing the constant term. What do I mean by constant? When we say a constant, we mean a number by itself. So in the formula, ax squared plus bx plus c equals 0, in that equation, that c that's by itself that doesn't have an x on it, that's called the constant term. And what I'm saying here is what happens if we have a quadratic where we're missing the constant term? So here it would look like this. Ax squared plus bx equals 0. A specific example of this would be something like 5x squared minus 35x equals 0. Do you agree that it does not have a number by itself, like plus 5 or minus 10 or something like that, right? It's just the x squared term's here, the x term is here, and then there's no other constant over here with it. And there's not a constant over here other than 0, okay? But if this would have been like 5, then this would not be this case. Because that 5 could be moved over, and then you would have a c over there. So we just have to have x squared term, x term 0. Now, what is the method for solving this? We are not going to do what we just did. We're not going to try and isolate the x squared. We are going to do Gcf factoring on the left side. So do you see a Gcf on the left? 5x. You take that 5x, you pull that out. So do you see I'm factoring left side? What would be in there? X minus 7 would be in there. Do you all agree with that? So what we've done is we've taken subtraction, we've turned it into multiplication. And now we use a very important property in algebra that says that if you ever have two things that multiply to be 0, one of them has to be 0. All right? If something times something is 0, then I guarantee you one of these has to be 0. So what we are allowed to do at this point is take the 5x, set it equal to 0, and then take the other factor, which is x minus 7, and set it equal to 0. So once we have factored, we're going to set up two separate equations from those factors. Each factor creates its own equation. And we solve each of these equations. Each of these equations are called linear equations, and we've done these before. Haven't we? How would you solve that for x? Divide both sides by 5. Good. And you get x is what? 0. Okay, so x is 0. And then over here to solve for x, you just add 7 to both sides. Get x is 7. There are two answers. Here's the original problem, right? There's the original problem. If I take either one of those answers and plug them in, it should be 0. So let's just try. If I replace x with 0, that's gone and that's gone, right? So this whole side is 0 and that's equal to 0 and that checks. Now what about 7? What's 7 squared?
49.
49 times 5. 245? Is that right? 245. What's 35 times 7? It better be 245.
245.
Okay, so if you plug in 7 here and 7 here, they will subtract out and give you 0, which checks out. Understand? No questions? Okay, how about this one? Negative 3x squared equals 18x. There's your next problem. Is this a quadratic equation? Yes. How do you know? Has x squared, right? And it has the equal sign in here. We're trying to solve this. Is it case 1 where we're missing the x term? No. Is it case 2 where we're missing the constant term? Yes, we don't have a number by itself, right? So what did I do on the last problem? I did GCF, right? But everything was on one side, wasn't it? Everything was moved over to one side, and then we did GCF. That's what you have to do first. You must get everything to one side. That way one of these sides is equal to 0. So how would you like to do that? Minus the 18x on both sides. So I'm going to subtract 18x on the left and the right. This is an important step. You have to get one side to be 0.